Joints are mechanical systems that are used for connecting two or more parts together, and bolted joints are those that are connected using a nut and a bolt, which are threaded fasteners. Their main functions are to hold the parts together in an assembly and to transfer forces from one part to another. This makes them a crucial aspect of a structure, despite being a small component of the design. They are seen in assemblies of different nature and sizes, such as in bridges and buildings, in electronic components, in automobiles, and even in orthopedic and dental implants. Threaded fasteners come in different forms. Two main types are bolts and screws. They both share the feature that the forces are transferred between the mating threads, but the main difference lies in their counter threads. In case of bolts, a nut is used which carries the counter threads. Typically, the bolt is held at rest using a spanner and the nut is tightened. In case of screw, it cuts the threads in the material during installation, so there is no need for a nut or an equivalent. In this case, the screw is rotated using an electric or manual screwdriver. In this course, our discussion revolves around bolt and nut assemblies, but most of the discussion can be extended to screw fasteners as well. Before diving into the mechanics of bolted joints, let's spend some time to learn the structure of bolt-nut assembly and the nomenclature. The nut and the bolt are the two main components that engage via threads cut into them. The interaction between the threads is where they transfer forces from one another. The nut and bolt heads are two surfaces between which the mating components are sandwiched. The portion of the bolt between the nut and the bolt heads is called as the grip length, and this is the load-bearing portion of the bolted joint. Now, let's focus on the threads of the bolt. The threads of the bolt is where the loads are transferred, and their dimensions is crucial to designing bolted joints. Three important terms related to threads are the lead, the pitch, and the number of leads. Lead is the distance advanced by the bolt along its axis for one full rotation. Pitch is the distance between the crests of two adjacent threads. Number of leads is the number of ridges that are wrapped around the bolt. Most bolts have one lead, in which case the lead and pitch are equal. While we are discussing about the design of a threaded fastener, it's worth noting that, in general, when we design a bolted joint, we don't really design the bolt itself. Instead, we design a bolted joint and we pick a threaded fastener from the existing ones that meets the design criteria of the bolted joint. So, we need a way of identifying the threaded fastener from their specifications. There are two commonly used ways of representing the bolts. They are the ISO metric system and the unified thread standard. In the ISO metric system, the representation starts with letter M, followed by the nominal diameter of the bolt, the pitch distance, and the length of the bolt, and all these measures are represented in millimeters. Here's a typical example for a bolt which has a nominal diameter of 8 mm, a pitch of 1.25 mm, with the length of the bolt being 30 mm. In case of unified thread standard, the major diameter is represented in inches, which is followed by the number of threads per inch, which is nothing but the reciprocal of the pitch distance. For bolts whose major diameter is less than 1/4 inch, the diameter is indicated by an integer defined as a standard. Here's a typical example for a 632 bolt, which has a major diameter of 0.13 inch and a pitch of 32 threads per inch. In both the cases, the threads are cut in V shape with an angle between the threads being 60 degrees. So, looking at the geometry of a typical threaded portion, this angle between two adjacent threads is called as the thread angle. The axial distance between two adjacent crests of the threads is called as the pitch of the screw. The bolt generally has two important diameters, the minor and the major diameter. The minor diameter is the distance between the opposing troughs of the threads, and the major diameter is the distance between the opposing crests of the threads. So, in case of both the ISO metric and the unified thread standards, the major diameter is used to represent the thread diameter, and the thread angle 2 alpha is 60 degrees.
Another important measure of diameter, which is considered as the effective diameter, is called as the pitch diameter, which is generally halfway between the minor and the major diameter. If only the major diameter is known, then one way of approximating the pitch diameter is to use this relation where D is the major diameter and P is the pitch of the screw. Another important parameter is the tensile stress area of the bolt. The tensile stress area is calculated by using the mean of the minor diameter and the pitch diameter. A number of tensile tests of threaded rods have shown that an unthreaded rod whose area is equal to the tensile stress area of the threaded rod has the same tensile strength as the threaded rod. Thus, when simplifying the geometry of a threaded bolt in a simulation and using a cylindrical bolt shank to represent its threaded portion, we need to ensure that the area of the cylindrical portion is equal to the tensile stress area of the bolt being represented. Tensile stress areas for standard threaded fasteners are often published in various design books.
Now that we've learned the nomenclature of a bolt nut assembly, let us now shift our focus to a bolted joint. A typical bolted joint consists of two parts or components that are sandwiched between a nut and the bolt. The bolt head and the nut remains in contact with the components and transfers the forces between them. When we tighten the nut by applying torque, it climbs the length of the bolt and applies compressive forces on the sandwiched plates and presses them together. As a result, the bolt head and the nut experiences forces in the opposite directions. All these forces balance each other out and maintains a static state of the system. If we look at the shank of the bolt, we'll notice that the reaction forces are creating a state of pre-stress and it is tensile in nature. So, when we tighten the bolt, there is a preload present in the bolt. This load is called as the clamp load or bolt preload. Since it's in a state of tension, it's also referred to as bolt pretension. Since the bolt shank experiences a tensile preload, there are chances that it may experience some plastic deformation and may even fail when this preload is too high.
To avoid this, we often design bolted joints based upon the proof strength and the corresponding proof load of the bolt. Proof strengths for common standard grades of threaded fasteners are published in various design books. In absence of any published data, proof strength can be approximated as 85% of the yield strength of the bolt material. This proof strength multiplied by the tensile stress area of the bolt gives us the proof load of the bolt. Thus, the proof load is the maximum load that a bolt can withstand without acquiring a permanent set. The recommended preload for most cases is between 75 to 90% of the bolt proof load.
Before we conclude this overview of bolted joints, it's worth spending some time to learn about the failure of bolted joints. There are several reasons that may lead to failure of bolted joints, and majority of them are related to the clamp force. We'll list 5 most common issues seen in such joints. The first reason is due to insufficient clamp force. If the bolt nut assembly is not tightened properly, it may further loosen during operation and may eventually come apart, which is considered as a failure. Also, some joints rely on the friction force between the bolt head and nut and the component surfaces, which is directly proportional to the clamp force. Such joints can fail due to very little friction. Another reason for failure is due to excessive clamp load. If the bolts are over-tightened, then shank may experience some plastic deformation, which will reduce its stiffness and may eventually fail in tensile mode if it's loaded up to its ultimate strength. Tension is not the only state of failure in bolts. In some joints that support shear loads, the bolt may fail in shear mode too when the external shear load is too high. It's important to make sure that the shear plane passes through the shank of the bolt and not through the threaded section. Fatigue failure is another cause for bolted joint failure. This is dangerous as it will appear without any signs. This occurs due to the cyclic loads that the bolts are subjected to. The fatigue can also be accelerated when the bolts are loosely connected. Finally, thread stripping is another mode of failure. When there's too much friction or adhesion between the threads, then they may shear and fail when torque is applied. Since threads are the critical load-bearing elements of bolted joints, their failure may lead to the failure of the bolted joint. This can be avoided by properly lubricating the threads before applying the torque. These are just some forms of bolt failures, but we can see how the preload present in the bolt plays a crucial role in their performance and reliability. With this, we can conclude the introduction to the bolted joints.